Okay, the training of today has been made in the frame of the NEMOSINE project, that is a research and innovation project funded by the European Commission, and is aimed to improve traditional cultural heritage storage solution to preserve visual and audio material by developing an innovative package. The primary goal of energy saving, extend consumption with conservation time of cultural heritage, absorption of the different industries, and new area of the consumption. The meeting, the webinar of today is the Acetic Acid solution and form for cultural heritage preservation. Today is include three presentations. One of them is focused on the World Day for Heritage, because the today training is coinciding with the World Day for Audiovisual Heritage. So the opportunity so we would like to highlight the importance of that day with some words that will be shared by the Instituto Valencia de Cultura. Then we will have a presentation about the metal organic framework as high-performance adsorbent for cultural heritage preservation that will be made together with Instituto Tecnológico from Portugal and the CNRS from France. Following, we will have the presentation from AIMPLAS concerning the development of open cell form for efficient gas absorption. At the end of the day, we will have a question and answer session. So you will have the chance to ask to the presenters clarification or further information after all the presentation. Presenters of today are Juan Ignacio Laos Rodrigo from Instituto Valencia de Cultura from Spain. He is the head of conservation of the Valencian Film Library Institute Valencia de Cultura. And he is the principal investigator of the entity in the European project NEMOSINE and Collection Care, both of them ongoing projects. We have also Katia Freitas from Instituto Tecnológico. She is a research fellow at the Department of Chemical Engineering of the Instituto Superior Técnico, and she has a master on characterization techniques of chemicals analysis from the University of Minho, Portugal. We have also Marinés Severino Neves. She is a PhD student at IMAP, Instituto de Material Poreux de Paris, and she is here representing the CNRS. And finally, we have Adolfo Benedito Borrás. He is from AIMPLAS, and he is the head of the Compounding and Material Research Development at AIMPLAS. Just for concluding my presentation, we want to let you know that for dissemination purpose, this training is recording and we will be publicly available. So notice that you cannot be, no one is able to see you. So the attendees are not able to, no one can see the attendees of the event. And if you have questions, please write directly in the chat, as you don't have the possibility to talk with the microphone, so the attendees. That is all for now from my side. So please keep on it with the progress of the project. We are arriving almost to the end of our activities. So these following months will be very active with our dissemination channels, the website of the project, the LinkedIn page, and the Twitter page. So that's all from my side now. I will not take more time. So I invite our colleague from Instituto Valencia de Cultura to make the presentation about the World Day for Cultural Heritage. So I will pass the floor to Juan Ignacio Laos. And thank you very much for participating.
Well, good morning, and thank you very much, Carolina, for your presentation. My mission today is to inform that today we celebrate the World Day for the Audiovisual Heritage. My name is Juan Ignacio Rodrigo, and I am the head of preservation in the Valencian Culture Institute, or the Valencian Film and the Valencian Film Archive. Well, this is the slide that the organization of the World Day is has been disseminated. And well, what is the purpose of this day? This is an initiative of UNESCO and the Council of Audiovisual Archives to encourage the task of audiovisual preservation, both professionals and institutions that we have the mission of safeguarding our heritage for future generations. Well, the topic of today, of this year, is a window to the world, as a recognition of the increasing presence and importance that the audiovisual content is playing in our lives to understand the world and our societies. More close to the task is the UNESCO statement, which they highlight the factors that threaten the safeguarding of the cultural heritage and the problems with the professionals of the preservation have to manage. Maybe the most important of all of them is technical problems. Well, it's important to remember that today, the 27th of October of 1980 was the date in which UNESCO adopted the recommendation for the safeguarding and preservation of moving images. This document universalize and supports the principles of the Audiovisual Archives commitment to the moving images preservation. This task started in the early 30s when were founded the first film archives. Then the problem was the practical of the practice of the cinema industry of destroying the prints of the films when the commercial life was in the end. The first decades of the cinema, there was an important debate on the recognition of the cinema of just a commercial product or as an art. Well, art and culture is the basis of the recognition of the cinema, of the importance of the cinema and the need of preserving it. Then the first film archives started to collect numerous negatives and prints of every work against also the composition and other factors that could destroy these materials, fires, etc. Well, the UNESCO's recommendation also points out the need of preserving these materials due to its weakness under specific technical conditions, and recommend to every state to safeguard the moving image heritage of each country. Then, in the same way that every state is preserving other cultural goods, and for this purpose, the recommendation of creating audiovisual archives in every country. Well, now, in 90 years later of the beginning of this task, most audiovisual archives we are preserving our collections in adequate technical conditions, but the degradation remains. Then, for us, it's essential research and innovation on materials and on preservation conditions. We have to to have in mind that for a century, for more than a century, cellulose derivatives were the base of most audiovisual production, cinema, photography, and the audiovisual archives we are facing huge problems with acetic acid and nitrate degradation. So this, the NEMOSINE project, as the NEMOSINE project is focusing on these problems and has developed solutions for its prevention and management that hopefully will be available soon. Then for us, in the day of the World Day for Audiovisual Heritage, we can celebrate NEMOSINE as a contribution for the audiovisual preservation. That's all. Many thanks. Thanks for your attention.
Thank you very much, Juan and Ignacio, for your presentation and for this interesting introduction and historic explanation about the importance of the preservation of cultural heritage material during the years. And it is also very good to know that the NEMOSINE is contributing for the preservation of this material with this promising research and development project. So, as said before, please keep tuned with the dissemination channels to get the results, to keep informed about the results reached by the project in the following months. Thank you, Juan Ignacio. So I will now give the floor to our next presenter. That is the presentation made through between Katia and Maria Inés. Katia from Instituto Superior de Portugal and Maria Inés from CNRS. So I will give them the. Okay, thank you.
Hello everyone, I'm Maria from Institut des Matériaux pour Eau de Paris, or AIMPLAS. In this training session, I will give you some insights on our participation in the NEMOSINE project, which focus on metal organic frameworks as performance adsorbents for cultural heritage preservation, and the results from the collaboration between AIMPLAS and the Instituto Superior Técnico, where Katia, who will also participate in this training, is based. So our presentation is divided in two parts. And in part one, I will talk about the synthesis and shaping of these performance adsorbent metal organic frameworks and all the steps required to incorporate them in the cultural heritage preservation applications. And in the second part that will be presented by Katia, it will be presented the characterization of these materials in terms of structure and adsorption properties. Recent cultural heritage artifacts, such as video and audio memories, have been found to be at risk of degradation on the account of the natural instability of their main component, cellulose acetate. This phenomenon results mostly from the released acetic acid, that it will have an autocatalytic effect, increasing constantly the level of degradation. Thus, acetic acid is a huge concern in conservation, and once it is present, the degradation starts and it's impossible to reverse it. It can only be slowed down. Some techniques are currently used in conservation to avoid this problem. However, they can be energetically demanding, such as, for example, the refrigeration systems. That adsorbents are seen as a promising alternative. The goal of NEMOSINE is exactly finding the best adsorbents that are stable and performant in these conditions. This adsorbent will then be incorporated in protective boxes built by a multidisciplinary team, meaning that they can include other components such as sensor or a night and full-on treatment in order to further extend the lifespan of the film reels. The main challenge in the use of adsorbents is the presence of water. Since water is highly polar, it means that it will interact with the adsorbent, impairing its use. This is the case of what happens for the currently used zeolites, since they are extremely hydrophilic. Thus, their interaction with acetic acid is impaired. Activated carbons are also considered for these applications. However, they emit dust that can damage further the artifacts, and they are usually characterized by low affinity with certain gaseous molecules. Thus, metal organic frameworks have emerged as an interesting alternative since their structure can be easily modulated to the restrictions, increasing the affinity with acetic acid while decreasing the affinity with water. In addition, these materials present higher pore size than zeolites, being advantageous for the adsorption of gaseous molecules. So what are metal organic frameworks? Metal organic frameworks are hybrid crystalline porous materials that are built from a diverse range of inorganic parts, the metal cluster, and an organic part, the ligand. Thus, these materials can be tuned for desired application, and in addition, they can present high affinities while having a high surface area and low regeneration temperatures. The different affinities can be achieved by modulating different features in their structure, depending on the applications envisioned. So, the different features that can be modulated include, for example, the pore size, the presence of active sites that can add chemisorption interactions, and this means stronger interactions, or by having a linker with certain properties, with the different features that can be modulated. For the purpose of conservation, initially two MOFs were found to be of interest. In this application, for example, MIL-140B, which is mainly an hydrophobic MOF, since it is absence of all groups in its organic fields. As you can see here, it is built from oxo cluster of zirconium that is connected to each other and forms a chain, and this chain is then connected to another chain by the aromatic decarboxylic ligands, delimiting 1D triangle channels that you can see in this animation. One other performant MOF is UIU66-2CF. This MOF is built it's similar to the UIU66, which is a MOF that is based on zirconium octahedral clusters that form lattice in an ideal 12-fold coordination with decarboxylic linkers, resulting in a cubic packed unit cell structure. The high zirconium charge and elevated connectivity of the nodes accounts for an exceptional chemical stability and thermal and mechanical resistance. In addition, since it has bulky CF3 groups in the linker, it increases the hydrophobicity compared to the non-functionalized structure, decreasing the affinity towards water. So the high zirconium charge and elevated connectivity of the nodes accounts for exceptional good stability of these materials, and the linker, the CF3, increases also the hydrophobicity compared to a non-functionalized structure of the UIU. So the two MOFs can be considered as hydrophobic, and they have been considered for the adsorption of acetic acid. So how are these materials obtained? These materials can be obtained with different synthetic types, as for example with solvothermal, where the reaction is done in an autoclave with high pressure and high temperature and usually requires aprotic solvents, while in the hydrothermal we only need water. These conditions favor the dissolution of certain aromatic ligands that are usually insoluble, and this promotes also the reactivity between the precursors. This synthesis is the case of the synthesis currently being used to form UIU66-2CF3. where fluorinated benzene dicarboxylic acid and zirconium chloride are added to an autoclave with dimethylformamide, and the modulator, acetic acid, is added in order to decrease the reaction kinetics and help with the crystal formation. Then the autoclave is placed in an oven for 24 hours with a certain temperature. However, this reaction generally suffers from a low use of the reaction volume due to the high pressure required, and this is associated with a low space-time yield. The space-time yield is a parameter used to evaluate the industrial potential of synthesis. This means the space that needs to be used, like the reactor volume, over time and times the yield. There are also other methods, such as electrochemical synthesis, which is already employed by a chemical company to produce these products for laboratory supply, meaning that they will be expensive. This continuous atmospheric method presents shorter residence time and has been reported for the production of several other MOFs. There are two types of electrochemical synthesis, such as cathodic deposition, which requires the addition of toxic expensive solvents. However, this can be problematic in larger scale, which I will discuss in some next slides. Or the anodic method that uses metal substrate and does not require the use of a counteranion for the structural formation of MOFs. However, this implies more difficult and expensive process. One more recent method that has aroused some interest is the mechanochemistry. Mechanical chemical synthesis is a solvent-free synthesis, meaning that we will not have to use toxic solvents, and this involves mechanical forces that break the intramolecular bonds between the chemical precursors, leading to the formation of new ones. Since MOFs are thermodynamically more stable, the cations that are liberated and the availability of linkers leads to their self-assembly. So, in all these cases, the success of the synthesis is proven throughout the different characterization techniques that we use, such as powder X-ray diffraction, infrared spectroscopy, or others that will be presented by my colleague Katia in the second part of this training. Another method that we employ in our group is ambient pressure synthesis. This consists on adding the precursors such as the linker, the metal source, and the solvent, and possibly a modulator to a reactor that is maintained at ambient pressure and that can be heated. The mixture is stirred, and when heated, a condenser is required in order to avoid evaporation. This can be done in a single setup or in a multiple setup when we are considering optimization. Depending on the material produced, after certain hours or days, we will have a precipitate of the MOF, which can be collected either by filtration or centrifugation. In our lab, we are able to do this synthesis method in milligram or in gram quantity, but we are also able to do this synthesis in pilot scale reactors where more than 100 grams or even kilograms can be obtained. With the vital information that we can have with this type of synthesis in the pilot scale production, we can evaluate the feasibility of this process in an industrial scale, meaning the tonnage scale. Thus, we see that the atmospheric pressure synthesis is relevant in order to produce MOFs that can be used in large-scale applications. So in the project NEMOSINE, we aim on finding a currently good performant MOF that can be synthesized with this procedure. So, in order to have a possible scale-up synthesis, we need to consider the most favorable synthetic conditions. This means, for example, considering the use of green conditions throughout the process. Thus, on one side, the metal source used should be carefully taught to avoid corrosion, that not only increases the risks in the facility, but increases also the capital fixed investment due to the higher price of the building materials. This is what happens when choosing, for example, nitrates or chlorides as counterions of the metal source. While if we choose sulfates, carbonate or oxides, we will not have this problem, but they are more difficult to solubilize. So usually also the solvents need to be carefully considered. In MOFs, the synthesis was previously done for a large majority with solvents that present a low health score, meaning that they can be toxic, carcinogenic, or have other health-related consequences. Furthermore, there are other properties of the solvents that can influence their greenness, such as the biodegradability, or if they are not biodegradable. And this can imply that we need further treatments in the downstream, which will also increase the price of the process. The linker considered is also a source of toxicity, so we need to choose a ligand that is not toxic, and it's also beneficial if it is bio-based, meaning that it can have a lower price. In addition, for both the linker and the metal source, it is beneficial if they are abundant. Finally, the process should also require low energy and not form any toxic byproducts, avoiding costly effluent pretreatments. Shaping is also something that should be done with MOFs in order to have something that is stable, that doesn't release powder since this is unpractical, and also leads to the loss of valuable material and can also contaminate sensitive materials, which is our case in the case of films. Thus, this can worsen the degradation state. Different methods of shaping can be explored. Usually the choice of shaping process is based on the form that needs to be obtained in order to have a more adequate product for the final application. This includes, for example, granulation, where we obtain granules, extrusion, where we obtain extrudate, pelletization, where we obtain pellets, thin films, foams, fluids, paper sheets, hollow structures, or even coating, where we can just have a surface that is coated with a thin film. So granulation, that we do in our group, is a facile and conventional method to form dense bodies via powder agglomeration without changing their chemical identity. This method is widely applied in the chemical industry, like in pharmaceutical, food industries, to store, to process, and transfer powders, but has also been employed to produce shaped materials for adsorption and separation applications, including shaped mock powders. Granulation processes can be characterized into wet and dry granulation. The wet granulation that we use, a volatile solvent, as for example water, is used to bind the powder particles into granules and then is removed by drying. However, if cohesion forces are not sufficient after drying, a binder can be added. The three general steps of granulation are wetting and aggluation, consolidation and coalescence, and attrition and breakage. So another method that we apply in our group is extrusion. Extrusion is done when a pressure is induced by the rotation of one or two screws that expels a paste formulation throughout a die with a specific size. The formulation of the paste is important, and the paste to be fed needs to have suitable rheological properties such as significant plasticity to allow the paste to be extruded throughout the die with sufficient cohesion that avoids the formation of surface and bulk defects in the extruded products, which can lead to fragilities in the structures, and then they will break and not be suitable for application. In addition, we spherinize our extrudates in order to obtain more condensed particles that are even more stable and that have a uniform size distribution. So finally, to confirm if our particles are stable, we do a compressive test where we measure the breaking point. So a sphere is put in the middle of two platforms and then it is crushed. So we change the strength with time and we see the point of crushing of this shaped material. Thus, when we obtain a higher value, we know that we have the best stability, and thus we need to find this value while maintaining the other properties. And like this, we'll have a material that will be performant but will also be stable, meaning that we'll have lower losses of material and lower contaminations of the other products such as the films.
Good morning. My name is Katia Freitas and I'm a researcher at IST in Lisbon. In this second part of our presentation, I'm going to talk about advanced characterization that we normally use in AIMPLAS and IST for the understanding of metal organic framework properties and capabilities. A wide range of state-of-art techniques can be used to investigate and characterize our performed MOFs. Techniques utilized for this purpose include power X-ray diffraction, infrared spectroscopy, SEM, TEM, adsorption studies, and computational methods. One very important technique used to confirm the MOF structure is the XRD. In an XRD experiment, a sample is placed into the center of an instrument and is illuminated by a beam of X-rays. The X-ray tube and the detector move in a synchronized motion, and the signal coming from the sample is recorded and graphed, where the peak related to the atomic structure can then be observed. This technique reveals information about the purity of our materials, and the pattern is considered a fingertip of the MOF. To analyze the organic and inorganic composition of our materials, we can use FTIR. This technique is based on the characterization of the energy levels and bond stretching of the chemical bonds. The primary goal of this technique is to measure how well the sample absorbs at different wavelengths of light and helps confirming the changes in the composition of our structure and the structure of our prepared MOFs. Gas adsorption is a well-established tool for the characterization of textural properties of our materials. Nitrogen absorption is widely used by the MOF community and consists in adsorbing nitrogen into the pores of our material and measuring the amount of physically adsorbed gas, and from this calculate surface areas and volumes. This method is important to obtain information about mesoporosity, microporosity, and surface areas of our samples. TGA is a thermoanalytical technique that measures the weight changes of a material at a given time and temperature. For the analysis, the material is placed onto a hanging pan, which is measured by a balance and situated in the seal furnace. The most common TGA experiment involves heating the material to a high temperature at a specific rate, recording the mass of the sample and the temperature of the furnace multiple times, allowing to obtain information about changes in the mass and also the rate of these mass changes as a function of time and temperature. In here, we can see a typical graph obtained by this method. The weight percent curve is primarily used to determine the amount of weight changes of each decomposition step in the MOF material. Normally, the first step, at low temperatures, is related to the composition of organic compounds. After, the mass loss is due to a residual solvent, and at higher temperatures is when we can see a metal oxide as a residue. Normally, when MOF materials are subject to very high temperatures, they tend to decompose or collapse. However, the removal of water and organic compounds from the pores of the material is important, and to achieve their full potential, most MOFs need activation. And this technique is a perfect method to evaluate how temperature will change and alter our material. Like Inês mentioned previously, the goal of NEMOSINE is to find the best absorbent for acetic acid adsorption. The material will then be incorporated in protected boxes to control cultural heritage degradation. Because of this, it's important to investigate absorption properties for our MOF materials. Although the techniques I previously talked are important to confirm structural and textural changes in our MOFs, after preparation and modifications, the assessment of their acetic acid performance and uptakes is extremely relevant. For this, adsorption experiments in a closed and under-controlled humidity chamber can be performed. This method acts as a screening test to understand adsorption behavior of our materials. The samples are placed in the sealed chamber at room temperature and under controlled moisture, and left around 90 minutes to equilibrate with the moisture content. After that, 1 microliter of acid acetic is injected through an injection port. The variation of the concentration of acetic acid inside the chamber is then recorded as function of time. This setup gives a quantitative measurement of the MOFs and provides a preliminary selection of the best materials to adsorb acetic acid under humid conditions. In here, we have some results from various MOFs tested in this setup. When we introduce the acetic acid, there is an increase of acetic acid concentrations, which originates the high-intensity peaks. And as soon as the material starts absorbing the gas, the concentration present in the chamber will decrease. MOFs performing well will lead the concentrations down to 40 after around 2 hours of the experiment. We also investigate the absorption of acetic acid and water as a single component, and for this we use a microbalance, and the measurements are performed by evaporating the corresponding vapor into the sample, which is placed in inside the microbalance, and recording the mass and pressure changes over time. These experiments are performed under vacuum and at a temperature of 25 degrees, maintained with a water bath. These measurements are performed under controlled temperature and also pressure. And this setup allows us to access the material acetic acid capacities and also study their hydrophobicity. Also in this setup, we can now do isotherms with different organic volatile compounds, such as acetone, acetaldehyde, methanol. By evaporating the vapor, we can control the mass increase over time and quantify how much acetic acid and water the material can absorb at a given relative pressure. Comparing this way the hydrophobicity of the material with their affinity to capture acetic acid. In here, we can see typical acetic acid isotherms obtained with this setup for different MOFs, and it's possible to see that the acetic acid adsorbed, it depends on the material tested. We can also study our MOF materials through breakthrough curves. Here we can see a schematic diagram of the breakthrough setup. The samples in this setup, on the contrary to the chamber and the microbalance setups, are activated under a flow of pure nitrogen. This nitrogen gas passes through a water bubble kept at 11 degrees, so we can maintain a moisture level of 40%. The sample is then kept under this flow for an hour and a half to equilibrate the moisture, and then the gas input changes to acetic acid mixture at a concentration of 500 ppm. This concentration was chosen since it was a compromise between the region of interest and the detection level time of experiment. As if we use a ppb concentration would mean waiting for hours or even days to saturate our column where the material is present. This packed column is also kept at controlled temperature with the help of the water bath. Here we can see a typical breakthrough curve. Actually, this is a result of a material that has very high affinity for acetic acid. As we can see, for the first 15 minutes, no acetic acid is detected, which indicates that all the gas is absorbed by the material, even the material being kept at a moisture level of 40%. The acetic acid signal starts to appear upon saturation of the column. From the breakthrough curves, the absorbed quantities can also be determined, since we know the flow rate, concentration of the acetic acid, and the time that takes for the saturation, so we can calculate the amount that was retained inside the material. If we compared the breakthrough result, the red squares, with a single component isotherm of the same material at a particular relative pressure, we can see that there is no difference between the breakthrough and the isotherm, which means that the presence of moisture did not decrease the acetic acid uptakes. It also means that the amount absorbed dynamically is equal to the amount absorbed in equilibrium. This is a very good indicator of the fast kinetics of adsorption under real-life application conditions, and we can also see that these acetic acid performance techniques can complement each other. Thank you so much for the attention.
Thank you. Thank you very much, Maria Inés and Katia, for your interesting presentation, showing the research made and the results gained during the activities performed within the NEMOSINE project. I don't know if you have something more to add, or if we can. I will remind to the audience that you can write questions on the chat, and by the end of the event, we will answer all your questions. So I will give now the floor to our following speakers, that is Adolfo Benedito Borrás from AIMPLAS. Okay, So Adolfo.
Hello, good morning.
Good morning.
You hear me?
Yes, very well.
Okay, perfect.
Yes. Okay.
Well, as I have introduced myself, I work from more than 20 years ago in polymers and plastics. And if you remember, my colleagues from seniors and University of Lisboa has been discussing and presenting the huge characteristic and performance of MOF materials as solvent materials, in this case, in the case of NEMOSINE project with the acetic acid. In my case, I would like to present you the effect of foams as supporting material for the solvent substances. As you know, when we use solvent materials, usually they are in powder form. The problem of this powder form, when we apply these materials to solve any gas, the problem is that we have a strong drop pressures that provoke that we have not enough diffusion of the gas through the materials, for example, and this is a huge problem in the case of membranes, for example, filters and other applications. In this case, we need to shape the materials to separate the particles, and as Marianne and Katia has explained very well, the shaping process of the MOF or other solvent materials is very critical for the final application. We can extrude it, we can make prelets. The objective of this solution is to have a good diffusion of the gas through the material, the solvent materials, without any pressure drop. An important supporting material to avoid this problem are the foams. The foams have several strong characteristics that can give and support the solvent materials as the MOFs, and that is to have to provide a mechanical stability, a thermal stability, to provide a good distribution of the small particles of sorbents to maximize the solvent performance, the gas solvent performance of these materials, and other advantages that we will be discussing around my presentation. Well, initially, I would like to present you the context in the framework of NEMOSINE project. As you know, an important problem of the European cultural heritage is that all the supporting material is made, we're talking about movies, photographs, posters, slides, are manufactured on cellulose derivatives from more than 1 century ago. We are talking about more than 80 millions of films based on these derivatives of cellulose, mainly cellulose acetate. The problem is that this material that is very good as supporting material for audiovisual information, the problem is that with the time, this suffer important degradation problems. From chemical point of view, we are talking about a hydrolysis process. This hydrolysis process affects more than 5% of the audiovisual material is in a critical stage. Usually this problem, this chemical degradation, is named with the very well-known name of vinegar syndrome. The vinegar syndrome is well known because during the process of degradation of this cellulose acetate, is released the acetic acid. The acetic acid smell. The smell is very huge, and this odor is a characteristic that put the name of vinegar syndrome. The signal mark of this vinegar odor is marks or put in attention the progression of this deterioration process. For this reason, also the presence of acetic acid in the movement of the cellulose acetate, the films, the movies, provokes the catalyst performance or behavior of this acetic acid. This means that as higher is the quantity of acetic acid in the environmental, faster is the degradation process of the films. This means that if we remove very quickly the concentration of acetic acid in the environment of the films, of the movies, we decrease the rate and the speed of the degradation process. For this, one of the main goals or objectives of NEMOSINE project is the removing of acetic acid in the environmental of the degradation processes. As has been explained in other training actions of NEMOSINE projects, we have a lot of different solvent materials that can be used for this purpose. We can talk about active carbon, zeolite, silicates, materials that has as common point the porosity. Porosity that is used to store or to trap the molecules, selectively the molecules of acetic acid. The good thing of the MOF metallic organic frameworks as solvent materials compared with these traditional active carbon, zeolites, or silicates is that they are more selective to acetic acid to compare with other, for example, other gases than the traditional carbon, zeolites, or silicates. Turning back to the problem, the vinegar syndrome is completely related to the use of acetate cellulose or derivative of cellulose in the movies or in the films on other applications. In this table, we can see the different materials that have been used during the last century. That this is the main problem or the main guilty of the vinegar syndrome. The different film formats have been used, from professional motion pictures, amateur rolls, microfilm, microfiche, sheet films, with all the different sizes, 35 millimeters, the huge 120 millimeters, and all the professional and amateurs formats. As you can see in this table, you can see that from the beginning, in the end of 19th century, the beginning, or practically the half of the 20th century, was used nitrate cellulose, acetate cellulose mainly, and these materials are basically the materials that suffer a lot the vinegar syndrome. In the end of the 20th century century was used polyesters supporting for films that don't suffer this vinegar syndrome, but the majority of the material we have at this moment in the archives are made on cellulose acetates or derivatives. Talking a little bit about the chemistry, as I have said, the acetic acid acts as a catalyst, an accelerator of many hydrolytic reactions. The water is one of the main impulsors or activators of these or triggers of this hydrolysis and vinegar syndrome process. For example, all materials that can suffer these hydrolytic reactions are the typical chromogenic yellow dyes, cellulose acetate, nitrate, and other polymeric binders used a lot in the movies and the audiovisual industry. Here we can see are very summarized mechanisms of this reaction that we have, for example, the cellulose triacetate. In the presence of water or humidity, we suffer this vinegar syndrome. We produce acetic acid and a break of the molecule of cellulose acetate into only monomers, cellulose diacetate. If we have long acetate cellulose polymers suffering continuously with the time this process, we produce acetic acid that catalyzes the reaction and accelerate this reaction. And each time we are cutting the polymer in smaller pieces of oligomers or polymers. And this is we will see finally in our movies as a completely deterioration of the material. This is a presentation of the life cycle of cellulose acetate polymers and factors. The life cycle is, well, from various sources we fabricate the cellulose. From the cellulose, all the derivatives of the cellulose, in this case, the cellulose acetate or nitrate, all the cellulose acetate-based products, and finally, with the acetic acid action or recycling actions, we have finally all the derivatives again. And finally, if we produce a complete disintegration of the cellulose acetate, we have monoxide, CO2, water, acetate, and more. Of course, the acetic acid is the main actor of this process, but we need to remind that the environmental factors can affect this process. We are talking about the presence of the sunlight, the presence of humidity, nitrogen self-determination, and more processes. Well, the main problem of this process is, sorry, okay. The main problem of these external factors is that to reduce the speed of vinegar syndrome process, we need to reduce a lot, in a very huge form, the external factors that affect to this reaction. This means, for example, that in the archive we are using environmental very low temperatures. They have important systems to reduce the temperature of the environment until between 1 degree, 4, 5, 6 degrees, not more. As you know, this represents a huge consumption of energy by year. If you develop, and this is the main goal and objective of NEMOSINE project, if we develop the energy requirements to reduce the speed of the vinegar syndrome, we are achieve an important goal, an important objective. And finally, really, the objective of use this kind of packages that we are developing in NEMOSINE project with acetic acid adsorbents is to reduce the speed of the reaction and to allow to reduce the requirements of environmental requirements in terms of temperature, in terms of humidity, and more and more. I have said, usually from the beginning, as talking about acetic acid sorbents, several important materials, classical materials as zeolites, as active carbons, have been used, or silica gel, for example, have been used from the beginning. Here in this table, we can see several values of the performance of acetic acid absorption. And for example, we can see that, for example, the zeolite has an important performance related to acetic acid absorption. The MOF, the metal organic frameworks, offer, compared, for example, with the zeolites, a better selectivity for specific gases, in this case acetic acid, compared with the zeolites. The zeolites, in other way, offers more thermal stability, more chemical stability, but it's not the case of this application. In this application, we have not working at extreme conditions. Au contrary, we need to control a lot of the conditions of the environmental. And in this case, the zeolites has not this advantage. The MOF and the selectivity and the performance as gas sorbents is very important in this kind of application. Well, I have said to use or to combine the MOF, the metallic organic frameworks, with a supporting framework is very important. In this case, I would like to focus my training action, my training in the foams as supporting material for this kind of absorbents. If we immobilize in a polymeric foam the sorbent particles that we are using, we can increase the performance of these materials, or at least to avoid important problems that I have commented until now, as the pressure drops. It's important to have accessibility of the acetic acid vapors to the absorbent, And the macroprocess structure that define this kind of forms is perfect to have the maximum surface accessible for the gases, for the acetic acid vapors. Also, as I have commented previously, the foams by itself provides a mechanical protection to the artifact and the own absorber. These were some of the different forms that we tried to use from the beginning of the project. It was very clear that the open cell structures were the best ones. You can see, for example, in the form number 9 or 10, you have the typical closed cell structures. In this case, in the closed cell structures, it's very difficult to have a good diffusion of the gas, of the vapor, because all the cells are closed. If you put inside of these cells our sorbents, our MOFs, we can have a very good performance, but we have not diffusion of the gas, and this is a problem. This is why we select from the beginning open cell foams. The 1 and 2 foams are very clear examples of open cells forms. We can see in these micro photographies that very easily, if we put on the sides the MOF materials, we can have a good diffusion of the gas through these foams, maintaining a bones, a good supporting material for the position of the MOF materials. The important is to define how to introduce the MOF materials inside of these foams. That I named the integration of the adsorbent on the foams. We have different, very well known methodologies on processes. Basically, we can divide this process in two: the impregnation of the absorbent material inside of the foam. This is a very easy and cheap process, but as we will see, this process has important or critical problems that finally has we have decided to remove this process from the final decision or the final material. In another way, we have a more complicated process, but I think is very successfully, has been working very well. That is the synthesis in situ of the foam material, taking the MOF sorbents inside of the process. This means that we are dispersing the MOF materials in the precursors, in the reactives of the foams, and we make the foaming process with the MOFs inside. This is that we name synthesis inside. In the first process, the impregnation of the sorbent materials inside of the foams, we can use electrodeposition processes or deep coating processes. In the other side, about the synthesis in situ, we can work in the typical polyurethane synthesis. We have make both the synthesis of MOF and the synthesis of the foam at the same time, and this will be a MOF synthesis under a polyurethane template. And finally, a new kind of foams that can take advantages of these requirements is the development of aerosols. Well, the first foams or system of impregnate foams with MOF material that we tried to prepare was the impregnation process. The impregnation process is a complete process that implies a compounding and impregnation and washing and drying and converting, while the foam in situ process has a mixing, a foaming and converting process. Basically, this is the diagram that represents all the steps related to the absorbent impregnation. First of all, we prepare a solution, a suspension with the MOF absorbent. The important thing related to this suspension is that we need to have compatibility between the solvent, yes, the liquid and the metal, the MOF, to have a good dispersion and to avoid the presence of agglomerates. Then we have the foam, and the foam previously is modified with a surfactant. The surfactant may be anionic, cationic, and this surfactant allows a good bonding between the MOF adsorbent and the surface of the foam. Finally, in a process that we name, if we make a deep process of the surfactant modified sponge in the liquid where we have dispersed the MOF sorbent, we make a process of self-assembly deep coating, and we have finally a sponge with an impregnation of MOF. In the bottom, we can see the process that suffers the sponge. First of all, we make a treatment by deep coating of the sponge with the surfactant. We have in the surface of the foam a surfactant layer, and finally, through a self-assembly process, we have the final coating of the surface of the sponge with the MOF material. In this slide, we can see different microphotographies of this process. In the A photography, the pristine, without previous to the treatment of the size of the foam. In the B, we have the previous surfactant pre-treatment, and then in the C and D image, we can see the coating in the surface of the foam with the MOF. This is the impregnation of the MOF that we are talking about. We can make this impregnation process, and we have tried with other, for example, other geometries. For example, in this case, we have like small balls, foams. That is a typical foam based on polypropylene. And you can see also that you can reach a very high grade of impregnation in the surface. For example, in the bottom, in the right side, right photography, we can see that all the surface of this kind of spherical particles that form the foam are completely impregnated and covered by the MOF crystals. Basically, summarizing this process of adsorbent impregnation, we can see that, for example, we have worked with polypropylene foams, and you can see the result, a macro photography of this impregnation and impregnation with polyurethane. What's the problem that we have found with this kind of processes, impregnation processes? Is that finally, if we measure the ratio or the quantity of the MOF impregnate into the foams is very low. We have not achieved more than 5% on weight of MOF inside of the foam. And of course, this low quantity limits a lot the performance of acetic acid absorption. We need to find new technologies to increase the interaction or to increase the quantity of MOF that we can include in the cells of the foams. For example, this is really the conclusion that we arrive with adsorbent impregnation. With these methods that we are reach low leadings, lower than 5% of MOF inside of the foams, and turning back to the methodology of measure or acetic acid absorption that has been presented by my colleagues of Lisbon University, we can see that practically after 2 hours of exposition to a concentration of acetic acid, practically this kind of foams has not absorbed any quantity of acetic acid. The acetic acid, after 2 hours, maintains practically its concentration. This means that practically we have a very low concentration of MOF, and it's not working as we expected. Another option that we have to work in the absorption of acetic acid beyond, for example, polyurethanes is the aerogels. The aerogels is a very interesting porous structure with the highest surface areas possible and very, very low density. In the case of aerogels, in the typical forms, we have a cell size around several microns. We are talking about cells around 50, 90, including 100 microns of cell size. In the case of aerosols, we are talking about cells or cavities in the nanometric scale. And this means that we can disperse better the MOF crystals inside this structure to separate and to have more contact surface of the sorbent with the acetic acid gas. This is basically the structure of these aerogels. In the aerogels, we can distinguish the macroporosity from the mesoporosity and the microporosity. To use this aerogel as supporting material for MOF sorbents, we need to increase the mesoporosity, because the mesoporosity, we are talking about sizes, cavity sizes between 5 nanometers, 200 nanometers, that maybe is a typical size that we can find in the MOF crystals. Why we are thinking to prepare MOF combined with aerogels? Because it's a very promising properties in terms of a lot of applications where the absorption is very important. For example, gas storage or catalysis process. The small size of the cavities of the aerogels provoke a better distribution of the MOF particles, high specific surface, porosity improve for the gas storage or gas absorption, etc., etc. How the aerogels are prepared? Well, aerogels, the preparation of aerogel preparation has an important critical point. The critical point of all this process is the drying. But previously to the drying process, we need to prepare that we name an hydrogel. Well, basically, the process of the fabrication of aerogel passes through a first step, that is to have a liquid precursor, where we mix disperse the MOF material. We have a salt MOF suspension, and then happens an important process that is the chelation trigger. This we generate in this solution with the MOF dispersed inside. We make a polymerization process. We make a polymer, a salt polymer in this, and this salt polymer is that we name a hydrogel. The hydrogel has basically 3 components: the MOF very well dispersed, the polymer, and the solvent. The solvent, if we are talking about a hydrogel, the solvent is the water, of course. Drying this material, and this is important, very important, is a critical process, critical step to remove. If we remove the water inside of this structure, we have finally the polymers and the MOF inside. This is the MOF-based aerogel. As I said, it's important to maintain this nanometric cavity structure that we can maximize the performance of the gas sorbents. The drying process is the fundamental or the critical step. We can dry the hydrogel with different processes. The most typical process is the evaporation in, for example, in an oven. If we do this, we collapse the system. We lost all the small, the nanometric cavities, and we have a typical compact material that is named zero-gel. This zero-gel is not suitable for the application that we are talking about. In the case of zero-gels, we have finally a monolith of MOF without the porosity and the gas diffusion performance that we are expecting. The aerogel is made by a process with extraction solvent that usually is made with supercritical CO2. And in this case, we make an exchange of solvent, and we exchange the water by air, and we have finally the aerogel structure what we are looking for. The problem is that this extraction solvent process is so expensive from energy, from money point of view, but another intermediate process to make these aerogels is the freeze drying processes. If we make the freeze drying processes, this literally a lyophilization process, we can control this nanometric structure. It's important, of course, the freezing process, because if we freeze in a not controlled way, the size of the ice crystals are so big, probably the cavities are so big. And it's important to control the temperature of the freezing process, the time, to control the ice crystal size. And finally, I have said the pore size and the morphology of the final aerogel. This kind of aerogels really are named cryogels. Well, the idea introducing these aerogels is to prepare MOF in aerogel structures with a polymer. The polymer that we are using as supporting of this aerogel structure is the nanocellulose. Several routes are well described to prepare aerogel based on nanocellulose. For example, we can use nanofibrillate cellulose or crystalline nanocellulose. In the case of nanofibrillate cellulose, we can manufacture or prepare aerogels by spray freeze drying processes. In the case of crystalline nanocellulose, we can use cross-linkable aerogels using, for example, hydrazide that can make this bonding between the cellulose crystals, make all the hydrogel structure, the polymeric structure, and then by the drying process that I have explained before, to have the final cross-linkable aerogel. And finally, another process that we can explore is to make crystalline nanocellulose aerogels by ascorbic acid reduction. It's very well known, this process, for make, for example, graphene aerogels, carbon nanotubes aerogels, carbon active aerogels, but has been explored for nanocellulose. Visually, we can see that we are talking about, we can make different processes for prepare this aerogel based on nanocellulose. And in the bottom, we can see the structure that we are looking for. We are looking for a structure with a very, very small size cavities inside, and very, very well dispersed the MOF crystals in these small cavities. Well, we did in the framework of the NEMOSINE project this kind of aerogels, as you can see in the photography in the right side, several materials prepared with the combination of MOF on nanocellulose. Well, basically, for the preparation of these aerogels, we use the lyophilization, the freeze drying processes. In terms that we have not really aerogels, we have in this case cryogels, I have explained. And as you can see in the performance of these foam materials adsorbents, we can see very impressive results. In the, for example, the blue test, we can see that finally, after the 2 hours of exposition with this concentration of acetic acid, we can observe we can practically reach a concentration of 20 ppbs. It's very, very, very small quantity. This means that this material show a very interesting acetic acid adsorption. The problem that we had with these materials that we can't see in this photography is the mechanical stability. The mechanical stability was very poor. The powder was released easily upon delicate handling of the samples. This means that this material was not suitable to include in the packages that we were developing in the NEMOSINE project. But finally, we work in other routes for preparing the aerogels based on nanocellulose. Based on initial work from Dimitri, Professor Dimitri, we prepared and we made several modifications of the process, as including the lyophilization, the freeze drying process. We prepared these cellulose-based foams via microwave curing. And with this type of processes, we reach until 80% of perfectly dispersed MOF inside of this nanocellulose foam structure. This is very different that we obtained from the beginning in the impregnation process, is that with difficulties we reach only 5% of MOF inside of the foam structure. In this case, we reach 80%, but we didn't try higher concentrations, because in this case we have a very good balance between mechanical stability, ratio of MOF, and temperature resistance. In the photographies in the bottom part of the slide, we can see the different characteristics of this MOF support nanocellulose foam. The reference foams without any quantity of MOF, the material with the 80% of MOF, and finally a micrograph photography where we can see the MOF crystals perfectly dispersed and distribute in the side of the cells of the nanocellulose foam. The problem is the MOF that we use, the crystals are so big. If we use a smaller crystal in nanometric scale, for example, in these cases, we will control better the size of the nanofoam cavity, and probably we will have better dispersion, and we could put more quantity of MOF inside of this kind of nanocellulose-based foams. Finally, we have different supporting actors for the MOF sorbents. We develop polyurethane foams with MOF pellets. We have cellulose foams with MOF powders, I have explained. And if we compare with the typical shaping process that has been explained by my colleagues Katia and Maria, we have the pellets. The three supporting or materials or structures offer us very interesting properties from acetic acid absorption point of view. We are talking about residual acetic acid in the chamber after 2 hours, around 20, 30 ppb, that is suitable for the application that we're talking about. The selection for another one depends on other factors than the specific acetic acid absorption performance. And finally, to finish this training session, I would like to say that, well, in NEMOSINE project, we have working with the foams as supporting material for maximize the performance of the metal organic frameworks for acetic acid absorption. But of course, this is the beginning of the way, because we know that the combination of the sorbent materials, in this case the MOF, with the foams has important application for the industry. For example, the foams with the metal organic frameworks can also be very important or critical applications, like for example, filtration membranes for water treatment, for example, to fight against the anti-fouling, the fouling generation in different surfaces. For example, we can work on catalytic membranes to increase the speed of different reactions and to use these structures, the foam structures, for example, in fixed bed reactors in chemical industry. Very basic, the gas storage performance, not only acetic acid, but also hydrogen, methane, or other gases important, for example, for fuels industry, electric energy industry. Another important application that I have found related to the combination of metallic organic frameworks and foams is to remove the microplastics in water, for example, to use, for example, also as face mask for gas contaminants, or for example, another application of these foams is for spill treatments in chemical industries. And that's all, basically. Again, I apologize by the problem that I had up in the beginning of my presentation, but I expect that finally this presentation or this explanation has been enough interesting for you. Thank you very much for your attention.
Thank you, Adolfo, for sharing your knowledge and also the details about the activities performed within NEMOSINE project. In fact, we have already 2 questions addressed to you. One of them is, do you have an idea about how long this absorption material can be used? So, and the second question is, how much time could they be effective, the adsorption material? I can hear you. I don't know if people can hear you.
I was mute, sorry.
Okay. Okay, did you hear the questions? Did you hear the questions?
Yes, perfect.
Okay.
I say that it practically is the same question because we are talking about the working time of this kind of absorbent, and really it depends one factor, that is the saturation of the material. If we saturate the MOF materials too quickly, we can't continue working with materials. We need to change the sorbent material to make, for example, in a vacuum chamber or a thermal treatment, to activate again the MOF material and to put again inside of the working place. In this case, the packages for conservation of the cultural heritage. It depends. Of course, we have not made yet the studies in long-term working because, well, we know exactly what is the saturation of the MOF materials in terms of acetic acid absorption, but we don't know exactly how it works in the medium that we are working on. This is a good question because the working time of this kind of solutions implies the periodicity that we need to change the sorbent materials. Is the same that happens with the water sorbent materials, the typical silica gel. When the color changes, this is an indication that we have saturated the silica gel, and we need to change this silica gel by another one. This is the same problem, but we don't have exactly the data to know exactly how many times, if we need to change these sorbents each 5 years, 10 years, we don't know exactly this time. But it depends on several factors, of course. The type of MOF that we are using, the quantity of MOF that we are introducing in our system, our packages, of course, depends on the concentration of acetic acid in the environmental. If we control from the beginning, because the production of acetic acid, because this is a is a autocatalyzed process. If we control from the beginning the emission of acetic acid in small levels, really we can increase a lot the duration of the MOF. If we put the MOF when the reaction is working from a lot of years ago, we have a very big concentration of acetic acid that which the MOF solvents cannot manage properly. In this way, if we control from the beginning when in the first stages, when the emission of acetic acid is very slow, probably this system, these sorbents, can work during a lot of years. For this reason, it's very important to put these sorbents inside from the first stage of the degradation process. If the material is very degraded and is emitting a lot of quantity of acetic acid, the duration, of course, of the solvents will be limited. Sorry, because I have not more specific answer or results about this, but basically this is the factors that we need to take into account.
Thank you, Adolfo. I think the question has been well answered. So you provided some details. I take the opportunity. Well, I can't see any other question for now. So if you have any further question, if you see the video and do you want to get more details or clarifications, please do not hesitate to be in contact with us through our channels, and also in the presentation of the speakers there are their contacts, so you can also directly contact them. I would like to let you know that the presentations and also the video of the today training will be available on the project website. And you will have the chance to see the video again and to better understand, if needed, the specific information shared by our presenter. So I thank all of you for your participation, and also I thank the presenter for the time dedicated and for the information shared with the audience. Here are our contacts. And also, please remember that in December, beginning of December, we will have 2 webinars addressed to the results of the project. So to practically use the results of the research made with the one from the point of view of archive, so like end users, and one of the webinars with the point of view of the industry side, so with the participation of industries. So please keep in touch with the project, keep visiting our website and our networks, as we are, as I